Awesome. All right. Good afternoon. Welcome. All right. So we finished up with forces on Monday. So today we're going to go ahead and start electric fields. Today we're hopefully going to get through electric fields. We'll talk about electric flux at the end, and then Friday we'll do Gauss's law, get through that. And we need to cover all of this because your next quiz, which is, so again, reminder, your first quiz is this Friday. Make sure you get it done. It's on charges and electric forces. The next quiz is not today, but next Wednesday, so the 22nd. Is the next one. That's going to be on electric fields and Gauss's law. If you can do electric forces, electric fields is just a very tiny step from that. So it's not much extra. Gauss's law is going to be the challenging part, so hopefully we'll have the time for that. If not, we'll make it work. Reminder that we do not have class this coming Monday. So that is on the syllabus. If you did not know that, there you go. Surprise, surprise. No class this coming Monday. It's some holiday of some sort. Martin Luther King. It's a good one. All the holidays are good. Anywho, we have spring break and then this coming Monday, Martin Luther King Day, and that's the only days off we have for the semester. So just for your own tracking, that's what we got. Okay, so we're gonna go ahead and get started. So, I very, very briefly talked about electric fields last time. I know these are magnets, which obviously, I'm going to tell you magnets do not make electric fields, but what's helpful here is it shows these kind of field lines, and we're going to be drawing a lot of field lines. So electric field discovered by Faraday. And so here's kind of some formal definitions of it. A field is the alteration of space around a particle. That sounds really fancy. Again, whether it's real or not, who can say? A field can be a vector or a scalar, but basically the important part here is that it's every point in space. So I'm going to show some pictures to show you what that kind of means. In this class, we're just going to do vector fields, so every single field we talk about, vector field, and all of these fields are going to result in forces. So we talked about the gravitational field, result in gravitational forces, electric fields, electric forces, magnetic fields, magnetic forces. And each of these fields acts on something different. Gravitational fields act on things with mass. Electric fields act on things with charge. And we'll get to magnetic fields that acts on moving charges. The important thing with what I just said is, so gravitational fields on mass, electric fields on charges, magnetic fields on moving charges. The things that the field affects are the same things which make the fields. So, gravitational fields, things with mass make gravitational fields which affect other things with mass. Electric fields are made by things with charge, and they affect other things with charge. And then magnetic fields, I'm going to keep repeating that one because we'll get to that and I don't want to add too much additional stuff. So, here's real quick basically what electric fields would look like we have two different kinds of charges, positive and negative. And so if I draw, well, that's awful. There we go. All right. If I draw my two separate charges, the dotted line here is to signify that we're treating them independently. So here's a negative charge. Here's a positive charge. The electric field due to a negative charge will point towards it. So if I pick this point in space, right above it, it will point towards it. As I get farther away, it still points towards it, but it gets weaker and weaker and weaker and weaker. And that should hopefully make sense because we said as charges get farther away, the force gets weaker. So by extension, the electric field that something makes gets weaker the farther you get away. So at every single point, there's an electric field which points towards it, and it gets smaller and smaller and smaller and smaller and smaller. One thing I want to point out here is that if, for instance, if I gave you a problem and I said, find the direction of the electric field at this point, what I want you to do is start the tail of the vector at that point, and in this case it's a negative charge, so it's going to point towards it, and then point it in the right direction. Very often what I see people doing is I ask for the electric field at this point, and people draw the electric field at the negative charge. Maybe they draw it like here or something like that. Don't do that. Draw it at the point I'm talking about, because that's where we want the field at, and you're going to see why. There's reasons we do that make our life easier. Alright, so negative electric fields point towards it. For positive, they point away from it. So at every single point, it follows that same rule where they get weaker and weaker and weaker and weaker. always pointing directly away from it. So if I pick some random point out here, it'd be some tiny little arrow. I mean, it's all relative. But they all point away. So pretty important concept. We're going to be using this a lot. Make certain you remember negative charges they point towards, positive charges they point away. All right. Great. So that's that. So, as I mentioned, so the purpose of the electric field is this is what we use to explain why a charge experiences a force. One thing, this picture is a little bit confusing. So actually, yeah. This picture shows two charges, and so basically what we're imagining is that there's some electric field in this space due to some other charges. So at this point, there's an electric field this way. At this point, there's an electric field this way. These electric fields are not due to this charge and this charge, okay? So I just want to clarify that because that could possibly make this confusing. This we just say we put them somewhere and there's some electric field. But if you have an electric field, going back to our equation, it's basically the force divided by Q gives you the electric field. I'm going to show this in the next slide, either the next one or the one after that. But the way you'll probably see this more often is the other way around, where the force equals the electric field times the charge. The important thing to know here, and actually I'll even do a nice little conceptual question here. So I'll finish this up and I'll give you a conceptual question. So electric field Q. So units of the electric field are newtons per coulombs. Where does that come from? Well, force is newtons, charge is coulombs. So newtons divided by coulombs is newton coulombs. There we go. Pretty simple. And then the magnitude is called the electric field strength. So units are newtons per coulomb. If you ever forget that, if you have this equation, hopefully you can remember that force is newtons, charge is coulombs, and you can just do it like that real quick. Newtons divided by coulombs. Okay, so my quick conceptual question to you all is I'm going to make an extra slide for this. What is the electric field exactly where what is the magnitude of electric field at point P in the image below? And then I'll show you what the image is. So point P, so I have a point charge here. It's a positive charge. Point P is dead center of that charge. So point P is exactly where that charge is. This is the only charge in the entire thing. It's one charge. What is the electric field exactly where that charge is? And I'll go ahead and give you all the equation for electric field because I haven't shown you that. E equals KQ over R. Spend a few seconds, think about it. This is a very important concept, which is why I want you all to have time to actually think about this. So electric field, KQ over R. I'll explain this equation more, but we're going to talk about this concept real quick because it's very important.
Is that scalar mean or vector mean?
We'll say what is its magnitude. So this could be a vector if I wanted it to, and I'd put that R hat there as well. Again, I'll show this equation later in a bit more formal sense, and we'll talk about it more. But that's what it is. KQ over R. Q is the charge. R is the distance from the charge to the point that we're considering. That's a K. K is the Coulomb's constant, the same exact one we saw before. All right, who has some ideas? Infinite. All right, who has some other ideas? Zero. Who has some other ideas? Undefined. Any other ideas? A second to zero. Here we go. All right. So in this case, if we did it mathematically, the distance would be 0. So we would do the limit approaches 0, which would say the electric field where a charge is located due to itself is infinite. Let's think of that conceptually. If that was the case, that would mean a charge would cause a force on itself. If anything causes a force on itself, that means it's going to cause itself to accelerate, and then who knows what direction that would be, and that would cause problems. So we can't have infinite. If we have 0, Zero actually works and undefined kind of works. The long and short of this is a charge cannot cause an electric field on exactly where it's located. It can't cause a force on itself. What that means is when we say this charge is here, we never evaluate the electric field that a charge generates exactly where it is located. If we had another charge here, we could totally say there's an electric field here due to this one. But we never say there's an electric field that a charge generates where it is exactly located, because that would mean it would cause a force on itself, which would mean that it would just erratically move all over the place, which would just be absolutely chaos, and it's just not how the world works. Not how we conceptualize it to make sense. So, a charge does not generate an electric field at r equals 0. Well, I'll write the words for it and then I'll put r equals 0. At the location the charge is placed. So, aka charge is 0. Or sorry, not charge is 0, r is 0. Because it has just consequences that don't make sense given how we observe the world. Again, all of physics is used to understand the world, so the rules should make sense in the world. That is a very important thing. Because and then we'll get to why that's very important. I mean, it's just that's the consequence. It can't cause a force on itself. All right, so here you go. Here's what I showed you before. It's F on Q is Q, E. So the reason I wanted to do that last example is because, and I'll go ahead and say this as well. An electric field, so if Q is, no, I'll do this first. Two charges. Sorry, I keep jumping back and forth, but I'm trying to think of the best way to say this. If I have two charges, a positive charge here and a positive charge here. The way we conceptualize this, we'll call this charge 1 and this charge 2. We say that charge 1 makes an electric field everywhere, okay? It makes an electric field everywhere. That means at the place where charge 2 is, there is an electric field, and again, it's exactly away from it because it's a positive charge. There's an electric field which points away from charge 1, because the electric field due to charge 1 doesn't really care about the electric field due to 2. At this point, it makes an electric field pointed away. The electric field that the first one makes results in a force on 2. So another way of writing this is the force of 1 on 2 equals the charge 2 times the electric field 1. Okay, and I could have put those in the opposite order. I could have put electric field 1, charge 2. But this is what's really important. This is experiencing a force from this one's electric field. It is not experiencing a force due to its own electric field. I'm really hammering down on this because this is a really common word problem that I could give you, is I give you these two charges, and then sometimes what people end up doing is mixing up these things. They'll end up putting the wrong charges in or putting the wrong electric fields in, and that's where you have to remember a charge cannot cause a force on itself, and so that electric field has to be coming from another charge. Okay? So, this then leads to our next thing. If the charge is positive, then the force it's going to experience will be in the direction of the electric field. So in our problem here, that I quickly drew out, charge 2 is positive, and the electric field points to the right, so the force of 1, 2 is also going to be to the right. Okay? Electric field 1. Yes. Well, in this case, it's a positive charge, so proton or some combination of extra positive charges.
Like you wouldn't use Q1?
No. So that's in this problem here. So if Q is positive, that is referring to the charge that is experiencing the force due to the electric field. Because again, if Q is positive, the force on the particle is in the direction of E. This is referring the charge that is experiencing the force, which means it is experiencing the force due to the other, the electric field due to the other charge. So charge 1 makes the electric field, charge 2 is the one that is positive and experiences the force in the direction of the electric field due to 1. A lot of wording there, but that's what it is. The other example, I'm going to draw the exact same problem down here. Well, I say exact same one, but now I'm going to make the charge negative. So our electric field here is still pointing to the right because it is due to the first charge. So this is again where a mistake that a lot of people can make. is I say find the force on charge 2 here on the bottom. And what they end up doing is they draw the electric field to the left because they're drawing the electric field due to the negative charge. That is incorrect because it's the positive charge which makes an electric field where this charge 2 is located, and that is what causes the force. Okay, so it makes an electric field to the right because positives always point away. The electric field due to positive charge, it always points directly away from the positive charge. But because this charge is negative, it is experiencing a force that is in the opposite direction. And again, this all makes sense. When you think about it, again, just always check your understanding. Two positive charges, they repel each other. Positive and negative, they attract each other. So our rule should always follow that convention. If you got a force here that was pointed away from it, then you're saying that a positive and negative charge repel each other. So always go back to the conceptual stuff. If your answer doesn't make sense, then you have the wrong answer. Or maybe some of the concepts are a bit mixed up in your brain. Either way. Okay. Any questions there? This is like some foundational stuff. We're talking about electric forces. This is going to kind of continue throughout the rest of the class. So we're going to spend more time on it, but if you have any questions now, please let me know. Okay. I'm going to kind of skip this problem here. Don't necessarily have time. So here's the equation for it. So here's the equation for it. We remember the equation for force. We talked about this. So 1 over 4 pi epsilon naught. Remember that is just K. If that looks weird to you, Coulomb's constant. And then we have the charge 1, the charge 2. Those are the two charges that we just imagined 2-point charges. I'll even draw them out. Here's charge 1, here's charge 2. 1, 2. Here is R1, 2. And so in this case, F1 on 2, F2 on 1. I'll give myself a bit more space so I can make them vectors. So 1 on 2, 2 on 1. Okay, so that's the reminder there. So if we said that the electric field is force divided by Q, then it is just going to be, get rid of one of those Q's. And this is where you have to remember which Q do you get rid of. Again, that's why I'm really trying to stress this a lot because a lot of students make this mistake. They put the wrong Q here. So if I wanted the electric field from this one, so the electric field that is causing the force 1 on 2, here's charge 1, here's charge 2. If I want the electric field that is causing F12, I need the electric field 1. So that's why I divide out Q2. I'm dividing out Q2 because the electric field 1, the electric field due to charge 1, causes the force on 2. So this is the one that the force is and I'll even clarify that. Charge experiencing force. So this is the charge that's experiencing the force. This is electric field which causes force. So the electric field which is causing the force is due to the first charge, charge 1. That's why charge 1 is still here. Charge 1 is the one causing the electric field, so we need to include that in there. If you're including charge 2, if you put charge 2 here, that would mean this would be Q2 times Q2, which means that you are saying that the charge is generating a force on itself. Please don't do that.
This is for electric field, right?
This is for electric field.
On the force, you would use Q2 and E1.
Yep, so this force would be used, this would be F12 equals E1 Q2. There we go. So that's why we're using that here. We're finding electric field due to 1, which causes the force on 2. And it's in the r hat direction. And this is all staying as vectors. So remember the r hat direction points in the direction. So this is R12. So r hat 12 points that way. And you can see that this quickly gives us the right answer. If this was a negative charge, it would cause it to flip directions. So R12 forces that way, great. If this was negative would go there, it would cause it to go the other way. Mathematically, if you want to do it, you can do it that way by plugging in the numbers, plugging in the negatives, or you can just do it magnitude-wise do the directions afterwards as a second step. That's what I prefer to do because it makes my life easier. Whatever you prefer, both are fine. Okay. I already showed this to you all. Electric field is everywhere. It's going to be stronger closer and weaker farther away because as R gets bigger, R is the denominator, gets smaller. So yes, R gets bigger, E gets smaller because it's on the denominator. Okay. I already kind of talked about all these things. Point away from positive, point towards negative. All right, great. Super simple answer, super simple question. So because I didn't upload the responses from Monday till today, I will not grade the ones today. They will not be part of your course grade. This is the last day basically to check to make certain that your clicker is working, everything forward. I'm gonna grade them no matter what. So, at what point is the electric field stronger, A or B? We have a positive charge, A is closer, B is farther away. I have the answers, A is point A, B is point B, C is not enough information to tell. There you go. Super simple question. I'll give you like 5 more seconds. The only time it should take is to get your clicker out. So 5, 4, 3, 2, 1. All right. Great. Everyone got it right. It's A. It's closer. Fantastic. Again, super simple. But the part where people forget this is when we have multiple charges. So that's kind of the last thing we're going to talk about. Whatever, great. Again, it's not worth points, otherwise I get that to you. Okay. So, not going to worry about that one. All right. Do I want to jump here? I'm going to jump back to that because we need to talk about multiple charges real quick. We'll talk about multiple charges. So what do you do if there's multiple charges? How do you find the electric field? So we wanted to find the electric field at this dot. And to the left of it, we have 4 charges in a square configuration. Positive charge in the top left and bottom right. Negative charge in the bottom left and top right. How do we find the electric field? It's actually very, very simple. I'll kind of jump back and I'll do this example. And that looks complicated. That's a lot of math. It's called the superposition theorem. Basically, I'll do it visually and then I'll go to the math because I think visually is easier. What you kind of want to do is you want to just treat one charge at a time. Unfortunately, I can't quite cover it up with my hand. So basically, we're just going to consider the charge at the top left first. So this negative charge up here, we're going to find the electric field at this point due to that one. So we'll call this 1, 2, 3, 4. So we find the electric field due to 2. Remember, it's pointed towards it. Because it's a negative charge, points towards it. So that's E2. Let's look at E1. Well, it's going to point away from it because it's a positive charge. And if all of these charges have the same magnitude, let's just say they're all, so that's Q, that's minus Q, plus Q, minus Q, all the same exact magnitude. This one is farther away, so we need to draw an arrow that is smaller. So that is E1. E3 is going to point towards it, so again, imagine like a straight line, and I need to make an arrow, same thing, it needs to be small. I guess roughly the same size as E1, that's close enough. E3, and then E4 is going to point away. And it should be the same size as E2, and it points away because it's a positive charge. All you then do is add up all these vectors. So this is why we draw the vectors at the point we care about, we draw the tails and we draw them away, because this is how it's going to make it easiest for us to add them up. This problem would be a little complicated. You would need to know the angles, you'd have to find the angle for this and that, and again, the math would be a little bit messy. But this is the concept for it. All I then do to find E is, so E, I'm going to write it in words because I don't want you all to get mixed up, is the sum of these vectors. So, to find the electric field due to a bunch of different vectors, do one charge at a time. Draw the arrow. Next charge, draw the arrow. Next charge, draw the arrow. Each time you are ignoring all the other charges. So when I did 2, I ignored all 3 of these. When I did 1, I ignored the other 3. I ignored 2, 3, and 4. When I did 3, I ignored 1, 2, and 4, etc., etc., etc. And you add them all up. pretty straightforward. It's like adding up forces, but these are electric fields. These are not forces. Another thing I really want to stress, if I ask you for electric field, do not give me the force. If I ask you for force, don't give me the electric field. And there's a really easy way I can make that hard for you, or like somewhat trick you, is I could say, here's a positive charge. Find the electric field exactly where that positive charge is. What people will immediately want to do is they will want to find the force on this charge here to the left. I did not ask for the charge here, the force on the charge here to the left. I asked for the electric field. And basically it's the exact same problem as I did here, because this charge again cannot cause an electric field where it is located. So, please read the questions, make certain you're answering the right thing. This is not me even trying to trick you all. This is just like you need to be able to identify if it says electric force or electric field. Okay, so how do you add the vectors? You add up the x components, you add up the y components, you add up the z components. Done. I mean, it's vectors. Again, we've done this, you've seen this. Now I just use the word electric field instead of forces. So you'd find all the x components, find all the y components, find all the z components. Okay, great. Practice time. What is the direction of the electric field at the dot? So the dot is located above them, kind of like an equilateral triangle with them. And the bottom left is a positive charge, bottom right is a negative charge, same magnitude, same distance from the point. Answer A is pointed up, answer B is pointed to the left, answer C is pointed down, answer D is to the right. Secret option E is none of the above. It's not really secret, it's down here, it's a little hidden. What is the net electric field at the dot? The electric field due to both vectors. Alright, gonna give you all like 5 more seconds. I'm still missing some responses, but want to get these in. Alright, so 5, 4, 3, 2, 1. Alright. So, let's do that problem solving process. How do you solve it when you're finding an electric field due to point charges? Do one charge at a time. So we're again on a more macro metacognitive level. How do you do this? We want electric field, and then you have to remember that concept. There you go. So look at the positive charge. We're going to call this one 1, and we're going to call this 2 to make my life easier. So you draw at the tail. We start here, and it's positive, so it points away. Great. That's the electric field due to 1. Electric field, okay, now we ignore 1 and we look at 2. It is a negative charge, still start our tail here, but we draw in the direction of 2. Then you have to recognize that there is symmetry involved. We need to add up these vectors. I didn't give you any angles or anything. You have to recognize the symmetry to see that the y components will cancel. They are both, so this one is pointed as much up as this one is pointed down. So if I drew this one down like that, it would be here, and this one would be here, and those two would cancel, and you end up with one big one like that. So the answer is D. Again, pretty much all of you got it. A few people did not, and that's okay. Just please make certain you review this. If you got the wrong answer, make certain you understand why. Work through it. All right. See which ones I have. All right. Next problem. What is the direction of electric field of the dot? I have a positive charge on the left, which I've already put 1 from last semester. Great, made my life easier. And then slightly to the right of this is a negative charge, same magnitude. So exact same magnitudes on both. And then my dot is to the right of both of those. A is up, B is to the left, C is down, D is to the right, E, the field is 0. What is the direction of the electric field at the dot? Q1 is farther to the left than Q2 is. All right, about 5 more seconds. So 5, 4, 3, 2, 1. Great. Okay. Same exact process for doing this problem. We're going to look at charge 1. Directional electric field due to that is going to be pointed to the right. I'm drawing it above the dot. Normally I would draw it exactly on the dot, but there's just not the room there. So, electric field 1. Electric field 2 is going to point, so we start at the dot. It is a negative charge. It's going to point towards 2, but it will be bigger because it is closer. E2. And again, ideally I would have started these tails here, but they're in the way. So, you do what you can. B. Okay, I'm going to give you all one more problem, then we're going to kind of move on to the next thing. I'm going to give you the exact same problem as this one, but just to really hit this home. Same exact problem. What is the direction of the electric field at the dot? But now on this dot is a negative charge. What is the direction of the electric field at the dot? The dot is exactly where the negative charge is. What is the direction of the electric field at the dot due to all 3 charges? Charge 1, charge 2, and my new and truly introduced charge 3. Yeah. What is the direction exactly at the dot? Direction of the electric field, exactly where 3 is located. All right, gonna give you all about 5 more seconds. So 5, 4, 3, 2, 1. All right, so let's go ahead and do this problem the exact same way we have done the other 2. Remember, we're finding the electric field at this spot. So to do that, we look at one charge at a time. So let's look at charge 1. Which way does the electric field point at this spot due to charge 1? Well, it points this way. The electric field due to charge 1 points that way because we're ignoring the other 2 charges. I did not ask for the force though. I asked for the electric field at this spot. So the electric, and remember how we do this problem is we ignore all the other charges. We just focus on one at a time. So we ignore that this charge is here. We ignore that this charge is here. All I care is the direction of the electric field at this spot. And because it's a positive charge, it's going to point away.
Wait, so the one before it was force?
The one before, these have all been electric field. They have conveniently been such that the electric field would point in the direction of the force if I put a positive charge there. This is a negative charge, which is purposely why I picked it, because if you tried to find force here on 3, you'll get the wrong answer. I did not ask for force. I asked for field. What is the direction of the electric field here? Again, follow the rules. We do one charge at a time, positive charge. Positive charge makes an electric field pointed this way. All right, let's do charge 2. We ignore 1, we ignore 3. We're looking at the electric field here due to the negative charge. It points this way. Last one, what is the electric field at this point due to charge 3 itself? 0, doesn't make one. So my net electric field is still this way. Now, the force will be in the opposite direction. The force on the negative charge, remember, negative charges experience a force in the opposite direction of the field. The force is this way. Force of 1 and 2 on 3. So if I had asked you for the force on 3, that would be the answer. But I did not. And that is why I said that before. Please don't make this mistake. I can easily just throw charge wherever I want you to find the force, find the electric field, and that's where everyone goes to force. You can have a field at a point, even if there's something on it. All right. Please make certain that makes sense to you. If not, ask me questions. Yeah, all right, everyone quiet down a minute. Here's the question.
So because we chose the negative as charge, we only look at what Q does by itself.
Yep. Even though it's a negative charge, we still follow the same process. We ignore every charge, it's just one charge at a time. What's the field there? What's the field there? Doesn't matter what's on the point, because we ignore it. When we're doing each one, we consider each charge independently. And then once you find the electric field, if you wanted to find the force on it, you would then just do that. Yep. Okay. So that's the main point. Oh, and the last thing I guess I'll talk about, and I'm going to start talking about flux as well. The last thing I'm talking about electric fields. This is a very important concept that's going to again carry throughout this class, carry in the future, depending on what you're doing. The electric field inside of a conductor is always 0. Always 0. Doesn't matter what shape it is. Doesn't matter what material it is. As long as it's a conductor, it has to be a conductor. Doesn't matter if it has a net positive charge. Doesn't matter if it has a net negative charge. The electric field inside a conductor is always 0. Again, assuming you're not pushing charge through it. This is I take an object, I give it a net charge. This is an electrostatic condition. Once we get to current, there will be an electric field inside a conductor. But in this case, we're not talking about current. We're talking about I put some charge there, I leave it there, it has time to move around. The reason being, if there was an electric field here, let's just make it up. Say there was an electric field here. What would that cause to happen? It would cause an electron to experience a force in the other way. So basically, if the electric field was not 0, that would mean you'd have charges moving around randomly. There would be electric fields, and there would be charges just moving around sporadically inside of a conductor all the time forever. And it would mean that you'd get a current. You'd have a current that would be flowing inside your system constantly. So basically, just pick a piece of metal, and that'd be saying at any point, every single piece of metal has some current flowing through it. That is not the case. What ends up happening is because the charges are free to move, you will get the excess charge on the outside because that is as far away from each other as they can get. That is the equilibrium setting, as the charges will move as far away from each other as they can. Turns out they'll actually, and this is a little bit weird because you'd be like, if they're moving as far apart as they can, why is there more charges on these sharp points? They do build up there, and if you do the math, you can find out why. But that's the gist of it, is this is the equilibrium position. They get to the surface, they build up on sharp points. This is why when you put aluminum foil in a microwave, you get this buildup of electric field there, you get this buildup of charge. Sharp points are kind of these, that's where charges will end up congregating. So if you want a really strong field, you want something that has a point. It's kind of a useful application of that. So very important, electric field inside a conductor is always 0, assuming you're not applying an external field due to something else. We'll get to that when we get to current. Okay. So that's just an important concept. All right, great. Whew. Semi-quick, well, it wasn't too quick, but pretty important concepts there. We're gonna switch gears here, move to Gauss's law. Gauss's law is going to be using electric fields. It's basically a tool to find electric fields due to objects that actually have a volume. Specifically, if you have a sphere, if you have a line of charge, or if you have a plane of charge, Gauss's law lets us actually find the electric field due to things that you would actually find in the real world, like an actual sphere of charge. So it's a bit more applicable. It's a mathematical tool basically, but it has some conceptual stuff we need to talk about. So today we're going to talk about flux. We're just going to talk about flux today. We're going to finish with that, and then on Friday we'll finish up with Gauss's law. Electric flux is basically just a definition someone came up with, where it is the amount of field lines that pass through a surface with area A. So this is the mathematical definition. So we use flux as this phi, capital Phi, equals the electric field dot product with the area vector. This dot product, if you all remember, you may have seen this before. You can take any dot product and write it as E, the magnitude of the, so in this case it's E and A, so magnitude of E times magnitude of A times cosine of theta, where theta is the angle between the two vectors. So any dot product you can write as that, and there's gonna be a reason why we need that angle. So one thing before I say that, when we say this area, we are talking about the area vector. Some of you may have seen area vector, hopefully you've seen it at some point, but I have seen that most students don't have a good understanding of it at this point, and that's okay. The area vector is the vector that is perpendicular to the surface. The trick to figuring out this vector that I found is helpful, so I will just pick an arbitrary thing. So here's my dot can, which I never use, but I'm going to use it now to tell you the area vector. So let's say at the top here, the area vector here, so it's flat surface. How do I find the vector perpendicular to this? I take my pencil and I put it on it. And that's the area vector. The area vector, I put it directly flat on it, area vector points up. You can see here, this is a 90-degree angle. My pen is a 90-degree angle with the top of it. Pick any single point in this and I can find the area vector on it by using that trick. This spot here, I put my pen on it. Put my eraser flat. You can see at this spot, it's a little curved. It's a curved thing, and I can move my pen around it, and the area vector changes. But as I keep my eraser flat on it, it is 90 degrees to the surface at every single spot. So if you are hung up on how to find the area vector, try to imagine it in the world if you can. I mean, if it's a sphere, use your fist, and take your pen and put it on your fist. Like, it's that simple. It is the vector that is perpendicular to the surface. We use this because it is generalizable. For instance, say we instead wanted to do it, we'd say, the vector is the thing that's on the surface, like this. Well, there is an infinite number of vectors that sit on that surface, so we cannot use that as our area vector because you have infinite vectors that describe that surface. There's only two vectors that describe the surface when we have perpendicular, the one this way, and technically you could have one pointed the other way. Generally, we'll pick the one that is within 90 degrees of the electric field. Okay, that just makes our life easier. So technically, I could have drawn the area vector pointed the other way through it, but we picked the one that's within 90 degrees just to make it easier to visualize and see. They're both correct, though. You'll both get the same answer. It'll be off by a sign, but we don't really worry about sign here too much. Okay? So the angle is the angle between the electric field. So there's there's an electric field made by something. If it's positive, if they're this way, it either means there's a bunch of positive charges here, or there's a bunch of negative charges here. This is how you would make an electric field pointed straight like this. Put a bunch of positive ones, put a bunch of negative ones, any combination of those. Positives will point away, negatives point towards. Either one's fine. You can have both, you can have either or. You can see here the flux depends upon the strength of E, the strength of the area vector, how big is your object, and the angle. Again, all this seems really weird. Electric flux sounds really funky. But literally just think about it. How many field lines are going through this area? The bigger I make it, the more field lines can go through it. The stronger the field, we imagine that as more field lines. The angle, here's the way to think about the angle. Here's a sheet of paper that I'm showing up in the air. Imagine I have an electric field going from left to right. So I have my object like this. This is when the maximum amount of field lines go through it. Is when the area vector, so reminder, we take our handy dandy pencil. Our area vector is also pointed from left to right. If our electric field is pointed left to right and our paper's area vector is pointed left to right, that angle is going to be 0. They're parallel. Cosine of 0 is 1. So that's the maximum. That is when you get the most number of field lines. As I rotate this paper, I get less of a kind of a cross-sectional area that I can go through until I get to this point when the area vector is now pointed up. Electric field is still pointed from left to right. No electric fields go through here. Electric flux, think of it like how much water is going through it. Just replace the word water with electric fields. How many of these things are going through it? So as I get to flat, if the electric field's from left to right, none of them go through it anymore. As I increase it, more and more and more and more and more and more go through it. Yep.
How do you figure out the direction?
How do you figure out the direction of the field? That'll be given to you in the problem. So the question was, how do you figure out the direction of the field? And this thing was given to you. And every situation will either be given to you or you will need to find it. Okay? Finding it would mean, again, if there's a bunch of positive charges here, maybe you'd have to calculate it. I'll never give you something you can't calculate the electric field for, though. So, there you go. That is one definition of flux. Electric field times the area, and it's the flux through this surface in particular. Okay? So any other questions? All right, we still got a couple more things I want to talk about with flux. Because, again, we have a lot to cover. Actually, we have one more clicker question I'm going to give you all. All right. Amount of field lines going through that. If E is a constant, so technically it's an integral. Because the electric field may not be constant, the area vector could change. I gave you a flat surface. So the flat surface, the area vector was the same here as it was here, as it was here, as it was here. But if I curve this surface, I take the piece of paper and I curl it, now the area vector changes, which means it is a much more complex problem, and you actually have to integrate over that surface. But in all the problems we're going to be considering, we're not going to have to deal with the integral. We're going to choose ones where either the electric field is constant, or the angle between them constant, or this term goes to 0. We're going to conveniently choose all our problems such that it's easy. That's what Gauss's law is used for. We only choose the easy ones. So if it's constant, E comes out, A is just A, and the angle is constant as well. So E has to be constant, the angle has to be constant, area is area. Okay, great. Let's do some math. We still got a couple minutes. I think we can get through a couple problems. So I gave you an electric field in this problem, which is 100 newtons per coulombs, and it's in the x-hat direction. So in this case, that means it's pointing from the left to the right. And I have a piece of paper which you are just going to have to conceptualize as, so I will show it to you visually. Here's my, oh, it's blue as well. Look at that. Electric field's going from left to right. The paper is like this. Okay, it's a little hard to draw 3D objects like this, but that's what this represents. Electric field left to right, paper straight up and down. And then the area dimensions of it is 2 meters by 2 meters. It's a square. What is the magnitude of the flux through this object? And I'll go ahead and tell you in all our problems we consider the flux to be a positive. Yeah, I'll say it's going to be a positive number. Yeah. There'll always be a positive number for everyone we do. So I'm going to give you a really simple, so this is a really simple one. And then next class I'll give you a really simple one, and then I'm going to give you one that's probably going to trick a lot of you, and we'll see how that goes. But that's pretty much what we're going to be covering for this bit. All right, 5 more seconds. I want to at least get the answers in so I can tell you what the right answer is. All right, so 5, 4, 3, 2, 1. Great. Okay, so how do we do this problem? We're trying to find electric flux. So what's given? Electric field in the area. We know that flux equals E. So magnitude of E, magnitude of A times cosine of theta. So we know E, A is just going to be 4. And the angle, the area vector is this way. Electric field is this way. This angle is 0. And so yeah, it's C. Good work. All right. We're going to talk more about flux next time, and then Gauss's law, and hopefully get through it all. Please ask me any questions if you have them. I want to answer your questions about anything. Doesn't matter. Yep.
So there's a point where you have the electric field to the right and the force goes to the other way.
Yes.